Okay, so here in this video, we're going to build up on those steps that we went through for describing the electric field of a charged object. So in this problem, we're going to consider a charged ring. Now, you can look at this ring as basically your wire that's been bent into a circle. So our problem is still one-dimensional, meaning our object can be described as a one-dimensional thing, even though it exists in a two-dimensional plane, namely our ZY plane as I've outlined here. And the question would be that if we know what the total charge of the ring is, and we know what the radii of the ring is, what is that electric field as a function of x? What is that? Well, so first thing is first, right? Let's start with our steps, right? Let's pick an arbitrary point on the x-axis. Let's say over here. And say that our electric field in the x due to some infinitesimal amount of charge. So let's go ahead and call an infinitesimal portion of this ring dq corresponding to some length dl about the circumference of the ring. So we see over here that the electric field dE will be formed. Now we can break this down into its components, dEx and dEy. Now maybe there's a way we can take advantage of symmetry here. So let's look at the opposing end of this ring as a finite or differential quantity. dq over here along a length of dl over here. We see a line about that to here makes an electric field that points this way. And this vector can also be broken down into its x and y components as well. And what do you know? We see here clearly that the y components are going to cancel out since they're in opposite directions, and they must be equal in length because it's the same amount of charge, the same distance away from the same point. Okay, and now we also can recognize that our electric fields in the x direction will sum. So we only need to worry about the differential equation that describes the electric field in the x direction. Okay, so we can further recognize something else about this scenario. There's a right triangle hiding here. Aha! So we see that one leg is, the radius r of this right triangle. The other leg is our distance x along the x-axis. So we see that our hypotenuse over here will be r squared plus x squared square root in lieu of the Pythagorean theorem. So now we can go ahead and describe our electric field only in the x direction. That's all we need to worry about. So let's define this arbitrary angle inside of our triangle as theta. Okay, now if that is theta, where should theta appear again with our electric fields? So in this instance, it's not too terrible. You see that theta is here. You see interior, opposite interior angles here. So you see theta ought to pop up here. So let's take the electric field over here, this triangle in green, and blow this up a bit. So we see there is DEX, there was DE, and then there was DEY. And this over here was our angle theta. So let's go ahead and translate our y component over here. So that looks a bit messy, so let me just move this label over here. So now we see that we can describe in this right triangle that DEX is equal to DE cosine of theta. Okay, so now we can go back and look at our other triangle for cosine of theta. So here we have x, here we have r, here we have this hypotenuse over here as r squared plus x squared, and we see that cosine of theta is equal to x over the square root of r squared plus x squared. And that's an appropriate substitution we can make into here. So now we see that our differential equation can be rewritten as follows. We can rewrite this as DEX is equal to DE times cosine, times x divided by the square root of r squared plus x squared. Okay, and DE, if we recollect what our differential equation was in our previous videos, we know that E is equal to K times Q over R squared, right? And we've already accounted for the direction. So this is just a magnitude that we're looking at. So we can likewise call this as DE, and I'm going to do away with some of the annoying bars, is equal to K dQ over R squared. Now for us, R squared is not terribly complicated. Here, our R is equal to the square root of R squared plus X squared. That distance from our charge dQ to our point in space where we want to know the electric field. So we can go ahead and rewrite this as DEX is equal to K dQ divided by R squared plus X squared. I can do away with the radical since this denominator is going to be squared, as we see over here, and this will then be multiplied by x over the square root of r squared plus x squared. Now we can even further simplify this whole expression and say DEX is equal to KX dQ divided by r squared plus x squared to the 3/2. Okay, so we'll continue looking at this in another video.